Today we're looking at Chapter 8, Chemistry Chapter 8, Energy Changes. Okay, if you take a look at this picture, you can see this forest is burning. So since the forest is burning, what we can observe is that a lot of heat is given out to the surrounding. A lot of thermal energy is given to the surrounding. Okay, so if you look at these questions, these are questions that tell us about a firefighter, how you can stop the forest burning. Now, this chapter, in the first section, we have 8.1, 8.2, and 8.3. Now, the first segment is exothermic, which is 8.1, exothermic and endothermic reaction. In exothermic reaction, energy changes are split into two sections. We have the exothermic reaction and endothermic reaction. At the end of this chapter, you'll be able to state that an exothermic reaction transfers thermal energy to the surrounding, and you should be able to state that exothermic reaction leads to increase in temperature of the surrounding, and you should also be able to state that endothermic reaction takes in thermal energy from the surrounding, and that an endothermic reaction leads to decrease in temperature of the surrounding. And then we should also be able to state that the enthalpy change is the transfer of thermal energy during a reaction, and we should be able to recognize that the enthalpy change is negative for exothermic reaction and is positive for endothermic reaction. So let's take a look at the first segment, which is endothermic reaction. To do a endothermic reaction, to determine whether a reaction is an endothermic or exothermic, we can do a simple experiment. How to do that? We take water and put in there, in a maybe a polystyrene cup, and then we can add any solid. We first of all measure the initial temperature of the water. We put a thermometer to measure the temperature, the initial temperature of the water before we add the solid. And after we add the solid, we dissolve, we stir it and dissolve it and measure the final temperature of the mixture. And if it increases, if the temperature increases, it means it's an exothermic reaction. If the temperature decreases, it means it's an endothermic reaction. Now let's take a look at this first experiment. We took water. Okay, we put a thermometer, we measure the temperature of the water, initial temperature of water, which is 28 degrees Celsius. Afterwards, we put some pellets of hydroxide, sodium hydroxide. We put pellets of sodium hydroxide. We stir to dissolve them in water. So that increases the temperature because the final temperature is now 34 degrees Celsius. So you can see the temperature has increased from 28 to 34. So now we find the difference in temperature. You see is 6. 34 minus 28, you get 6. It means the temperature of the water has increased by 6 degrees Celsius. Heat energy equal is given out to the surrounding. Because the temperature has increased, it means heat energy is given out from here, from here to the surrounding. So it means the reaction is an exothermic reaction. It's an exothermic reaction because heat energy is given out from the surrounding. Now let's take a look at experiment 2. This time around, we are not putting sodium hydroxide pellets. This time around, first we measure the temperature of water, 28 degrees Celsius, and then we add a solid ammonium chloride, We stir it to dissolve it, and then we measure the final temperature. When we measure the final temperature, we got 22 degrees Celsius. You can see that the temperature did not rise, the temperature actually decreased. Okay, so you find the difference in temperature. It means the temperature has decreased by 6. The temperature has decreased by 6. When temperature of the final mixture of the surrounding mixture is reduced, it means the reaction is an endothermic reaction. It means the temperature of the content, if it's reduced, the final mixture is reduced, it means it's an endothermic reaction. It means it's an endothermic reaction. Okay, so this is an experiment that tells us about endothermic. So expect something like this in paper 6 to be able to write an experiment to explain that concept. Now let's take a look at what is exothermic reaction. An exothermic reaction is the reaction that involves the transfer of thermal energy. Thermal energy means heat. That involves the transfer of thermal energy to the surrounding. Any reaction like burning a piece of paper, you're burning a piece of paper, or you do a campfire, if you close to it, the heat is transferred to your body. So any of those type of reactions where heat is being given to the surrounding is called exothermic reaction. In exothermic reaction, temperature of the surrounding increases because the system gives heat to the surrounding. So the temperature of the surrounding increases. The product are at a lower energy. We're going to show that when we do energy diagram. The product are at a lower energy because we're giving energy to the surrounding. Energy is given out, so the product is at a lower energy. So the energy change is a negative for exothermic reaction. Energy change is a negative. Okay, energy of reactant minus energy of product. Energy taking in to break the bond minus energy in making new bond is a negative. So once you get a negative, it means it's an exothermic reaction. So anytime delta H is the energy change. Energy change means enthalpy change. It's the same thing as enthalpy change. Okay, we use symbol delta H to show the energy change of reaction. Okay, energy of reactor and energy of product. The difference between energy of reactor and energy of product, once it's a negative, it means it's an exothermic reaction. It means an exothermic reaction. It means the energy of reactant is greater than the energy of the product. So the resultant effect is a negative. And here, activation energy, EA, or we sometimes we write A small e. Okay, it depends. Okay, the activation energy is needed to start a reaction. Activation energy is needed for a reaction to start. You have to boost this in order for the reaction to start. Now, the activation energy is negative. So, exothermic reaction is equal to total energy absorbed for the bond breaking is less than the total energy released for making new bond. Okay, when we write equation, you will see. When we write equation, you will understand this concept. Energy, the total energy for breaking a bond, before you can form new bond, you have to break the old bond. For example, let's say hydrogen. Let's say you have hydrogen. Okay, can I? Let's say you have hydrogen react with oxygen to form water, for example. I just wanted to show bond breaking and bond forming. Okay, the total energy absorbed in breaking bond is less than the energy released in making new bond. Is that okay? The total energy absorbed to break bond is less than the energy in making new bond. Now you have to break bond before you can make new bond. Okay, so that's for exothermic. For exothermic reaction, energy in breaking bond is smaller than the energy in making new bond. The energy in breaking, let's say sodium hydroxide react with hydrochloric acid, you have to break this bond. What's the bond in sodium hydroxide? You break sodium away from hydroxide, OH. You break this bond. And in this one, in this other reactant, you have to break the hydrogen bond away from the chlorine bond. Okay, so you break them into bond. Okay, each one to be separate. Na, Na, Na plus. If you are putting in form of ion, Na plus, and then OH minus. You break this one, hydrogen and chlorine. They are all separate. Then new bond will be formed, which is the new bond will be sodium chloride. One from here will take on the one from here to form sodium chloride, and the hydrogen here will take on OH here to form water. So you break this bond first before you can form new bond. You break the bond first before you can form new bond. Okay, so in exothermic reaction, we're saying the energy in absorbing breaking this bond of reactant is smaller than the total energy released for making new bond, which is the energy released in making sodium chloride and water. Okay. Now, exothermic reaction. In exothermic reaction, you have to absorb thermal energy from the surrounding. Thermal energy is taken from the surrounding. You don't give, you take. This one, you take the energy from the surrounding, and the temperature of the surrounding will decrease. Of course, because you've taken the temperature, you've taken the energy from the surrounding, temperature of the surrounding will decrease, and the products are at higher energy level. The products are at higher energy. The products are at a higher energy. Unlike this one, the products are at a lower energy. The products are at a lower energy for this one, for exothermic reaction. For endothermic, the products are at a higher energy. We're going to see it in a diagram. A good example of a reaction that involves exothermic is when you take ammonium chloride reacting with water. Ammonium chloride reacting with water, we take energy from the surrounding to form the product, So here, the delta H is a positive number. One easy way of differentiating exothermic and endothermic is that delta H for endo is positive, and delta H for enzo is a negative one. The activation energy is needed to start a reaction also, and this one, the activation energy must be positive. Okay, let's move on to examples of exothermic reaction. Example, physical process. Condensation is an example of exothermic reaction. I know you'll be wondering why is condensation? Because condensation is cooling. You are cooling something that is already hot. So as something is cooling, it's giving out the heat it has. It has heat. It's giving the heat out to the surrounding. It's giving the heat out to the surrounding. So it's losing heat, giving it out. So condensation is cooling. Freeze also. Freezing the temperature you already have, you're giving it out to the surroundings. You're losing it. You're losing it so that you can become blocked. So freezing is a physical process that is an exothermic reaction. Condensation is exothermic reaction. Freezing is exothermic reaction. Dissolving a hydrous salt, a hydrous copper 2 sulfate in water. When you dissolve salt in water, a hydrous salt in water is also an exothermic reaction. It's also an exothermic reaction. Then dissolving acid, especially consider acid in alkali in water, and alkali in water. When you dissolve acid and alkali in water, is exothermic reaction. It's what? Exothermic reaction. Now let's take a look at chemical reaction that involves exothermic, like combustion reaction, like burning. Like you drive a car, you're burning fuel. When you burn it and you combustion of fuel, or you're burning firewood, or bush is burning, all manner of burning or combustions are all fall under category of exothermic reaction. Respiration, respiration process whereby you release the carbon dioxide, you take your oxygen, right? You release carbon. Respiration is an exothermic reaction. Respiration is an exothermic reaction. Now, corrosion of metals like the rusty of iron. Rusty is an exothermic reaction. And neutralization reaction, all neutralization reaction. What is neutralization reaction? Neutralization reaction is the reaction of acid and alkali. Acid reacts with alkali to form salt and water, or to form salt and other compounds. Is an example of exothermic reaction. Now let's take a look at endo, physical process and chemical process of endo. Now in endothermic reaction, physical process like evaporation. Evaporation, you are taking heat from the surrounding, right? You take the heat so that the top particle of the water will gain more energy in order to be able to escape. You have to take the heat from the sun to heat this thing. Even boiling, you have to take heat from your gas cooker to heat the water. So you're taking heat from the something. So all these are endothermic reaction. Dissolving some ionic compound like ammonium chloride in water. Ionic compound, when you dissolve them in water, they are or azo. These are physical processes. Dissolving crystallized salts, also copper 2 sulfate in water, they are all endothermic reaction. Now, the chemical reaction is like one is photosynthesis. Photosynthesis is an endothermic. You have to keep this in the back of your mind. Photosynthesis is an endothermic reaction. Any thermal decomposition. Decomposition like break calcium carbonate, breaking a big lump sum of solid into smaller constituent is an endothermic reaction. Photosynthesis, thermal decomposition, and reaction of sodium hydrogen carbonate with acid. Anything sodium hydrogen carbonate with acid is an endothermic reaction. Now let's take a look at the enthalpy change, delta H of a reaction. So enthalpy change is the total energy of product minus total energy of reactant. Finish. First, you calculate the energy of the product. Then you say minus, you calculate the energy of the reactant. So energy of product minus the energy of reactant, you get the enthalpy change. You get what? The enthalpy change. Okay? You get the enthalpy change. Energy of reactant is the energy in. Energy of product is the energy out. Energy of reactant is energy in. Energy needed to break the bond of the reactant. Energy of product is the energy in forming new bond. Energy in forming new bond. So this is energy out. Energy in forming new bond. So energy out minus energy E, or energy in minus energy out, you get the enthalpy change. You get the enthalpy change. And this is the symbol delta H, and the unit is kilojoules. It's kilojoules. The name is enthalpy. Enthalpy. Okay, this is enthalpy. So enthalpy change, this is the name. When they ask you the difference between the energy, thermal energy of reaction, the process is called what? You say enthalpy change. Enthalpy change. Okay, we move on to the next one. Okay, let's quickly move on to the next one. Here is an example. You say when 1 mole of iron reacts with 1 mole of copper 2 sulfate, iron reacts with copper 2 sulfate in aqueous solution, 150 kilojoules of heat is given out. Here the word given out. 150 joules of heat is given out. If it's given out, it means it's an exothermic reaction because heat is given to the surrounding. So it's going to be, this energy will be minus 150. This energy will be minus 150 kilojoules. Okay, so you write the reaction. Iron reacts with copper 2 sulfate to form You know, iron is higher than copper in the reactivity series. So iron will displace copper from here to become iron sulfate, iron 2 sulfate, right? Copper plus copper, okay? So the reducing agent is iron, right? Reduces this copper 2 sulfate to copper. Reduces copper 2 sulfate to copper. So because it's higher, iron is higher in reactivity series than copper, it will displace copper from this position, and if you take that position, iron will come and sit here. It become iron 2 sulfate, become iron sulfate, right? Plus copper. Copper will not be on its own as a solid. Okay, this is a this is the energy change. Now, so this is an exothermic reaction. You can see it's a negative. It's an exothermic reaction. Okay, once this enthalpy change is given to you, you'll be able to tell whether the reaction is exothermic or endothermic. Then, when 1 moles of solid ammonium chloride decompose. Once you hear the word decompose, you already know it's endothermic. Decomposition reaction, they are endothermic. Photosynthesis, they are endothermic reaction. Okay, once you hear decompose to form ammonia gas and hydrogen chloride gas, 136 kilojoules. So this is going to be a positive number because it's a decomposition reaction. Therefore, it's an endothermic reaction. It's an endothermic. So energy change is this. You write the reaction, you write the equation, and ammonium chloride is NH4. Ammonium is NH4. Ammonia is NH3. Ammonia is NH4. So one hydrogen decompose means to break into 2 or into more substituents. So it will break. One hydrogen will be emitted from here to react with this chloride to form hydrogen chloride gas and ammonia. NH3 will remain here, ammonia. So when the decomposition occurs, it's called enthalpy. It's called the endothermic reaction because the enthalpy change is positive. Enthalpy change is positive. Now let's quickly we go to the next one, next section 8.2, which is the reaction pathway. The reaction pathway. Energy changes. Remember, we said they are subdivided into 2: exothermic reaction and endothermic reaction. Okay, and we say energy in this one, the energy of the reactant is greater than the energy of the product, or you can say energy of the product is lower than the energy of the reactant. Okay, energy of you can say vice versa. Energy of the product is lower than the energy. So when you're drawing the diagram, energy against progress of reaction, you draw this one to go down. The product will be down this way for exothermic. Energy of the product, you can draw a line here to show the product, or you can use this one to represent the product. Energy of the product is lower than the energy of the reactant, or you say energy of the reactant is greater than the energy of the product. So energy is given out to the surrounding. Delta H is negative because smaller minus big, you get negative, right? Smaller number minus bigger number, you get negative. So it's going to be a negative. Let's say here is 5 and here is 10. 5, which is the product, because the energy change, enthalpy change is product minus reactant. So 5 minus 10, because you know in the graph, here will be like 5, here will be like 10. 5 minus 10, you get negative 5. That's why it's a negative value. Energy change is a negative one for energy for reaction diagram pathway, reaction pathway diagram. So if you show it in the diagram, the product side is lower than the reactant side. Therefore, endothermic, the product side is way higher than the reactant side. So that's why this one is positive, because 10 minus 5 will be positive 5. So the energy change will be positive for this one. Now let's move on quickly. Let's move on. Sorry. Okay. Reaction pathway diagram for endothermic reaction. I think we've already explained this one. If it's higher, if the product is higher than the reactant, is endothermic. If the product is lower, is exothermic. Okay. Okay, take a look at it. For enzo, the product is lower than the product side is lower than the reactant side. The product side is lower, so the energy change will be negative because product minus, like I already gave the example, like minus 5 or minus whatever this one is. This value, let's say is 2, and this one is 7. 2 minus 7, you get negative 5, right? So you can see you're going to get a negative in the energy change. Your energy change is the energy of the product minus the energy of the reactant. So you got to get a negative. So energy given out to the surrounding, this one, energy is given out because you are having a negative value. Energy is given out. So reactant have more energy than product. Reactant has more energy than product. So product has less energy. Why? Because the energy is wasted to the surrounding. The energy has been wasted to the surrounding. Energy has been given to the surrounding. Energy is given to the surrounding. So the energy of the reactant is bigger than the energy of the product because during the reaction pathway, energy has been lost to the surrounding. That's why the energy of the reactant is bigger than the energy of the product. Okay, that's for this one. Now, for endo, this one is not clear, but it's the same thing. So 8.3. 8.3 activation energy. Activation energy, we want to look at activation energy. In activation energy, we will look at is the energy between the reactant to this slope, this height. But for this endo, is the way all the way from where the reactant is, you draw it up to this place. Okay, maybe we'll use another diagram to show. So this is the activation energy. Now, between where the reactor is and where the product is, that place is called the enthalpy change. This one is called the enthalpy change. Between where the reactor is and product is, it's called the enthalpy change. Let's look to go to the next slide. It will be clearer there. Okay, let's go to the next slide. It will be certainly be clearer. Okay, let's see this one. Activation energy. First of all, let's define activation energy. What is an activation energy in an energy reaction, in energy change? Activation energy is the minimum energy that colliding particle must have in order to react. The minimum energy, for example, if you want to jump a height of certainty now, or you want to kick a ball to be able to pass through this height, the minimum energy that is needed for this ball to jump up and roll over this height is the activation energy, the minimum one. We are not saying the maximum, the minimum one. But if you hit like table tennis, when you are playing table tennis, there is a net in the middle, right? So if you give it something less than the activation energy, it will hang in your court. You know, the ball will not bounce to the other side of the court because you gave it, you didn't give it activation energy. The minimum energy that you need for the ball to be able to cross the net to the other court of your opponent is the activation energy. In reaction chemistry, we say activation energy is the minimum energy the particle needs in order for them to collide. The minimum energy for the particle needs in order for them to react. You know, if the particles don't gain energy, they don't react. They're just there. But in order for reaction to take place, you need minimum energy to activate to make the reaction to happen. That minimum energy that is required for particle to start to react is called the activation energy. So a reaction will occur only when the reactant particles possess energy equal to or more than or greater than the activation energy. Either the minimum is there, you get the activation energy, or you get greater than the activation energy in order for reaction to take place. Now here is the reaction pathway diagram for exothermic reaction. Remember we say in drawing exothermic, please don't confuse, you should know how to draw. First of all, you draw a graph, a two-dimensional graph like this. You call this vertical side energy. You call this one progress of reaction or reaction pathway. Some people call it reaction pathway or progress of reaction. Then you come here, you draw the reactant here. The product must be lesser for exothermic reaction. You bring the product graph lower than that of the reactant graph. Okay? When the energy change is this minus this. Whatever value this one is minus this one, you get energy change, which means it's between here and here. Look at it. You draw broken lines out. The energy change is only between here because sometimes in the exam they ask you to show the enthalpy change. Energy change means enthalpy change, okay, delta H. It's just from here to here for exothermic reaction. For example, activation energy is from reactor to this height, to this gallop height. The energy needed in order for the reaction to overcome this barrier. Okay, so here is from here. In the exam, they ask you to draw it. You can even draw it from the middle here. You can draw an arrow here to show activation energy. You draw E, capital E, small letter A as activation energy. Okay, you can use it. Capital E, small letter A. Or you can use capital E, substrate, capital A. This is the activation energy. It's from here to here, from this place to this place. Okay, which is shown out here to here. This is the activation energy. The minimum energy required for this reaction to occur, for this reaction to take place, is the activation energy. Now the energy change or enthalpy change is the energy of the product minus the energy of the reactant. Remember the reactant is here. If you draw the line out, this one, product minus here, minus this value, you get the enthalpy change. So you must be able to show it in diagram, progress in diagram, okay? Now let's go to the endo one, This is for exothermic reaction. For the endo, this is the diagram for endo. Let's take a look at the diagram for endothermic reaction. For endothermic reaction, this is the reaction pathway diagram for endothermic reaction. This is the reactant. The reactant is lower than the product. Exo, the product is lower. For endo, reactant is lower than the product. Okay? So the activation energy for this one to take place is big. Look at it all the way from reactant all the way to the up. This is the activation. The minimum energy required for the particle to start to react is called the activation energy. The minimum energy required for the particle to start to react is called the activation energy. Okay? Now, what is the enthalpy change? Enthalpy change is the difference between the reactant and the product, meaning only from here to here. Okay? Because if you trace this one out, if you trace this one with a broken line, from this level, you trace it to the product, this is the enthalpy change. Okay, so this is the plot. This is the plot of the endothermic reaction for energy pathway, reaction pathway for endothermic reaction. We should be able to say this. Now we go to the next one, 8.4, which is bond breaking and bond forming. This one requires some mathematical calculation, which I hope, since we cannot write, I hope we can be able to show it. In energy changes, they are always divided to two, exothermic and endothermic reaction. Okay, the total energy here is less than 0, which means it's a negative. This one is greater than 0, which means it's positive. Okay, now let's move to the next one and see if we can have a calculation or something to show. Okay, bond breaking and bond making. Now, you see this nitrogen is diatomic. Okay? What causes energy changes in chemical reaction? When nitrogen reacts with hydrogen to form ammonia, heat is given out, right? In order for that to happen, we have to break this bond. You know this nitrogen to nitrogen triple bond. You know it's a triple bond. Okay? This is not writing, so it's difficult for me to show you. It's a nitrogen to nitrogen triple bond. Nitrogen to nitrogen triple bond. Why is it a triple bond? Because nitrogen, atomic number is 7, right? First share is 2, second share is 5. It requires 3 electrons to complete second share to be completed. So this is needing 3 electrons, so it's a triple bond. It's a triple bond. Nitrogen to nitrogen triple bond. So you need energy to break this one into this. That's called bond breaking. Energy needed to break the reactant. You have to break this nitrogen into its bond, constituent bond. This hydrogen you have to break. There are 3 of it. So you have to break the hydrogen into 3. Hydrogen to hydrogen is single bond because hydrogen just has 1 electron, right? So hydrogen to hydrogen is single bond. So you just write, you draw one line. You draw hydrogen and a single line to another hydrogen. But there are 3 of it, meaning you do 3. There are 3 of it, meaning you do 3. Okay, sorry, it's laggy. I don't know, but I hope you understand. Hydrogen to hydrogen, single bond. So I will do 3 like this: H to H, another H to H. 3 of it: H to H, H to H, H to H. That's the meaning of these 3 molecules. You have 3 molecules of it. You break the bond, you have 3 molecules of it. Now it is when you've broken this bond, you broke this, that they will form ammonia. So 1 nitrogen will take 3 hydrogen. Now you have 6. You have 6 hydrogen, right? 3 times 2 is 6. 1 nitrogen will take 3, the other nitrogen will take 3. That's why you have 2 molecules of ammonia. 2 molecules. 1 nitrogen take 3 hydrogen, another nitrogen take 3. So 1 nitrogen here take 3 of this, and the second nitrogen take 3 of this. You know this 6, 3 times 2 is 6. That's what you have here, that's what you have. So this bond forming, you are forming a new bond. This bond breaking, what happens here is bond breaking. So energy in breaking these bonds is called the energy in. Energy in. Energy in forming new bond is called energy out. Enthalpy change is energy in minus energy out. Enthalpy change is energy in minus energy out. Okay, so this one you can see is negative. This is exothermic reaction. This one, you can see is positive, this endothermic reaction. You break this bond, nitrogen to nitrogen triple bond, oxygen to oxygen double bond. So they are reversible reaction. We'll talk about the forward reaction and backward reaction in chapter 9. Okay, the rate of reaction, we'll talk about it in chapter 9. Now, it's a reversible reaction, meaning the reaction can go both ways. Okay, so you form nitrogen react with oxygen to form nitrogen monoxide. Okay, and then you break this bond, you form new bond. So enthalpy change is energy in breaking these two bonds of this reactant minus energy in forming this new bond of the product. Okay, energy changes in reactions are caused by making and breaking of chemical bond. You have to break this bond first before you can make this new bond. You have to break these bonds of the reactants in order to form new bonds of the product. Is that okay? Now let's show you with diagram. You can see here we break the nitrogen triple bond. You have triple bond here. Okay, this for the nitrogen and this for this one. You break nitrogen, oxygen, double bond. You see, you break the bond. This you need energy to break it. You need energy to break this one, this nitrogen to nitrogen triple bond. You need to break it. This nitrogen dioxide, this nitrogen. You know, it's a diatomic molecule. Nitrogen is a diatomic molecule. Diatomic means they have two atoms. Okay, or halogen plus few nitrogen, oxygen. They are diatomic. Okay, so you need energy, you need heat energy to break this bond into individual. There are two of them bonded together. You break them into single ones. Same way you need energy to break this one. So that energy is called energy in breaking bond. And once the bond is broken, they will form new bond. You now see one of these pairs with one of these, and one of these pairs with one of these. This nitrogen monoxide. Now, nitrogen monoxide is formed, new bond. So energy in breaking this bond minus energy in forming new bond is the enthalpy change. If it's negative, it's exothermic. If it's positive, it's endothermic. Now let's move on. How can we tell if a reaction is exothermic or endothermic? It's when overall energy change, enthalpy, is equal to total energy absorbed for bond breaking minus the energy released for bond making, bond. You know, remember I said energy absorbed for breaking bond is the energy of the reactant. Okay, it's energy in. We call it energy in. Total energy absorbed in breaking bond is the energy in, and energy forming new bond or forming product is the energy out. Energy forming product is the energy out. So enthalpy change is energy in minus energy out. Enthalpy change is energy in minus energy out. When the one absorbed is less than the one released, it's called exothermic reaction. When the energy absorbed is greater than the energy released, it's called endothermic reaction. Okay, let's move on. Okay, it's laggy somehow. I have to take it step by step. Okay, now let's take a look at this. It said the equation for the reaction between nitrogen and oxygen to form nitrogen monoxide is this. Look at the equation for the reaction. Okay, the enthalpy change is positive. Now, because it's exothermic reaction, the reactant is at the bottom, and the product is up, right? The product is up because it's endothermic reaction. Reactant is at the bottom. So you have to break this nitrogen to nitrogen triple bond. You know, I already explained this. You have to have nitrogen to nitrogen triple bond. When you break this one, you get nitrogen to nitrogen triple bond. And then you break oxygen. You get, why is oxygen to oxygen double bond? Because the atomic number is 8. Okay, first share is 2, second share is 6. So it's requiring 2 to be added to it to make what? To make 8. So since it's looking for 2 to be added to it to make 8, it becomes oxygen to oxygen double bond. So one atom of this reacts with one atom of this to make the product, to form new product, nitrogen monoxide. And the other one, with this one, you get another. That's why we write 2 here. That's why we say 2 molecules of it, meaning two of these type, 2 of its kinds. Okay? So let's move on. Now, it says calculating the enthalpy change of the reaction using bond energies of the reaction, using bond energy. Okay, now, this is the very important exam question in Cambridge IGCSE. We need to know how to do this. They will give you the bond energies. Okay, they will give you a table for bond energies for each of them. You see this hydrogen, we break it, will be hydrogen to hydrogen, but because there's two molecules of it, you are going to multiply by 2. Oxygen is oxygen to oxygen double bond, you are not going to multiply by 2. And then you form water. Water, you have OH, OH, 2 of it times 2, you are going to have OH, 4 of it. You're going to have 4 of it. OH here is one bond. OH to this side is another bond. OH to this side is another bond. OH to this side is another bond. So that's why you're going to have 4 OH for water. Every OH, you're going to have 4 for water. Why? Because there's 2 molecules of water. One takes on one hydrogen. One O takes on one hydrogen. The same O takes on one hydrogen. The same oxygen take on the second hydrogen. So you have 2 here. This energy breaking this is just is hydrogen. You take the hydrogen to hydrogen value, multiply by 2. Multiply by 2. So it's like this plus this. This is the energy for this one, 436. 436, since is 2 of it, 2 molecules of it, you just say 2 times 436. You get the energy for this one. Plus, you do this one. You do for this one, for breaking this one. What's the energy of this? O to O. Whatever is given, it will be given in the table. You say plus that value. Okay? That the total for the reactant is called energy in. The total for the reactant is called what? Energy in. Then what you get for the product is energy out. To get enthalpy change, you say energy of the reactant minus total energy of the product. Energy of the reactant minus meaning energy in minus energy out. Energy in minus energy out. Is that okay? Energy in minus energy out. Energy in minus what? Energy out. Is laggy, okay? I want to move to the next slide. Okay. Now, like I told you, they will give you a table of values. Like I told you before, they will give you what? A table of values. They'll give you a table of value. Now, let's take a look at the table. Say, calculate the enthalpy change for the reaction between hydrogen gas and oxygen gas to form water. Calculate it. Now, they will give you H to H. This is hydrogen. 2 atoms of hydrogen. Look at it. It means this. This is for hydrogen. This one, only this H2. It means this one. It's 436. Right? Right? Now, remember this H to H is 2 molecules of it. So we're going to use 2 to multiply 436. Because there's 2 at the back, 2 molecules of H2. So we're going to multiply by 2. So this value multiplied by 2 plus the value of oxygen. What's the value of oxygen? O to O double bond is 496. So you add them, you get the energy in. Energy in breaking this bond. Energy in, it's called the energy in. Now let's take a total energy absorbed for breaking the bond is 2 times 436. 2 times, why we multiply by 2? Because 2 molecules of this one. Okay? 2 times this plus, this one does not have 2 at the back. Does not have 2 molecules. It's only the atom. Oxygen to oxygen double bond. So you say plus that value, you get this one. This is called energy in. This value is called energy in. They are all in kilojoules, okay? The value, this is energy in. Now we calculate energy out, which is energy forming new bond. Energy forming new bond. Energy out. So you write the energy in. The total energy in is 1,300 and what? 1,368. The energy in. Now let's calculate the energy out. Remember, for water, we said there are 4 molecules of OH. First, look for OH. Where's OH? OH is 463. There are 4 molecules of it. You know, we showed you. We broke it down. OH, here is 1 O. We go to 1 hydrogen. You put the O in the center. It's just like I can't write. That's the problem. You put O in center. To the right, it bond with 1 hydrogen. To the left, it bonds with another hydrogen. Okay, this is the water molecule, if you show it in bond form. And there are 2 of it, so multiply by 2, 4 OH. So what you just do, you look for OH, the value, you multiply it by 4. You multiply this value by 4. Okay, so you say that's how they got this 4. 4 times 463 you get 1,852. This is the energy out or energy in making new bond. Energy out or energy in making new bond. To calculate enthalpy change, this delta H is the energy in breaking the old bond, that's energy in, energy of reactant, minus energy of the product. Energy of the reactant is 1,368, minus energy of the product. Energy of the product is 1,800. This is going to be a negative. You can see smaller number minus bigger number. So you're going to get a negative. So when you say this minus this, you get negative 484. So that this kilojoule mole whatever per mole per whatever. Okay, so the energy change is a negative. So this is an exothermic reaction. This reaction is an exothermic reaction. If I get positive, if I say energy in minus energy out, or energy in breaking the old bond minus energy in forming new bond, if I get positive, it becomes endothermic reaction. Would that be endothermic reaction? Okay. So I think with this we've come to the end of this chapter. We've come to the end of this chapter. So we hope you understand our class. Thank you very much for joining us.